Good morning, everyone. Welcome back to Project Management. Today we are going to be doing our How the Earth Moved project, and this class is the Computer Network Support class, class 18. So without further ado, let's begin. Our first group is Jasper's group.
Hello everybody, my name is Jasper. This is my team. This is Mike, Alex, and Robert. And today, as Alex said, we will be presenting some slides on how the Earth moves. It's a video on YouTube. So without further ado, let's begin. Yeah, next slide. Okay, and my subtopic today is going to be on the Earth's rotation. As you guys know, the Earth is always rotating. If it wasn't, we'd all be dead. Why does it spin? Next slide, please. Okay, so it all goes back to how the Earth was formed in the first place. The universe was once nothing but hydrogen and dust. And does anybody know what hydrogen is, by any chance? Anybody?
Element? Is that element?
Yeah, that's right. Perfect. Hydrogen is an element. It's probably like the most abundant element in the universe. It has it's highly flammable, right? And it makes up about 75% of the mass of the entire universe. So the force of some major events such as a supernova cause the gas and dust to spin and flatten, thus creating the planets of our galaxy. And this right here, this little GIF, is the representation of a supernova. So why does the Earth spin again? Essentially, the Earth spins because there's no force out there to stop it from spinning. As I said earlier, the Earth is already spinning from that supernova, and the momentum of all those planets and all the dust and all the gas, it's keeping everything just going because there's no gravity out in space. Everything's just continually spinning. The motion of the Earth orbiting around the Sun also plays a role in why it spins. So imagine this being the Earth, and then this being the Sun. The Earth is rotating counterclockwise around the Sun, thus creating more momentum, keeping the spin going. The moon's gravity also plays an effect on the spin, which it slightly affects how fast it spins. It actually slows down the rotation a little bit. And there's also something called the Great Attractor, which is it's an unknown force known by from scientists. They don't know what it is. It's like a giant magnet, pretty much. Next slide, please. And here's a video of how it looks when the Earth is spinning. Usually you see like videos of the galaxy moving, but the Earth is actually spinning in the galaxy. Everything, the sky's staying the same. It's actually the Earth spinning, so I can get rid of the sky. So as you can see, it looks kind of trippy, but this is how it should actually look because the Earth is what's rotating. The sky isn't. It's the Earth. So, yeah. And I will pass it on to Robert.
Alright. So, hello, my name is Robert. I'll be talking about the subsolar point. So what is the subsolar point? Subsolar point is exactly when the sun's ray hits exactly at 90 degrees on the Earth, which is shown here. What it causes is it causes shadows to fall directly below the object. So, makes this leveler look a little bit funky. And there's a sculpture in Hawaii by Isumu Noguchi that shows how this effect works. So it's any other day, the sculpture would cast a shadow which is a little bit swirly and off-center, but when the sun is directly above that position, it will cast a perfect circle since there's no bends outside when it's the sun's directly above it. When and where does this occur? The solar point occurs between the Tropic of Cancer and Tropic of Capricorn. This is due because of the Earth's tilt. And also only occurs in Hawaii in the US, and it just shows where Hawaii is right here. So why do we perceive these photos as weird? It's all based off of perception and what is normal to us, and shadows help us understand the depth and size of an object. So as you can see here, from the videos that we should have done, it looks like these objects have been photoshopped into the photo when it's actually naturally occurring. And I just brought in an illustration of the illusion. So looking through here, the A and B look like they're different shades due because of the shadow, and our brain's trying to perceive that, because that's what we perceive as normal, because shadows will make things darker, when in reality, it's actually just the same shade. So some fun facts is subsolar point is also known as a Hyman Dune in Hawaii, which translates to cool sun. The rest of the world calls it time of zenith. That subsolar point always moves westward due to the Earth's orbit, and as of right now, subsolar point is over the north side of Argentina. And then you go to this website, you go track where it is occurring, and you can also press on locations on where it will occur and when. I will now pass it off to Mike.
All right. So, gravity, right? What is gravity? It's being affected. You're all being affected by gravity. Everybody has their own gravity. Anything that has mass has some sort of gravitational pull. So gravity is the weakest of the four fundamental forces of nature, and we're all affected by it. Everything in the universe is affected by it, whether it's a big pull or a small pull. And even though Earth is really big and it seems like it's really hard to stay on here, in reality it's really not. You can overcome gravity really easy, right? You can jump, tossing a ball, just like that. So, if you go next slide. So how does gravity affect time? The simplest way I can put it is the faster you're traveling through space, the slower time goes for you, right? So one thought experiment you can put in your brain is, if you're sitting on Earth and somebody is in space, they're in a rocket and they're flying by you at near the speed of light, you would see that light to them, if you're observing them, seems to be bouncing at an angle slower than you. Because if you're stationary, light would seem to bounce directly up and down, right? You're not moving, everything's stationary, it's all relative. But if somebody's in space and they're moving extremely fast, time and light is going to look warped, right? It's not going to be relative, it's not going to be normal. So that person is going to be experiencing time slower, because it's taking, really what you can explain it as, it's taking time longer to catch up with them if you want to do. That's about as simple as I can put it. Next slide. And that is also known as time dilation. That was figured out by Albert Einstein. There's gravitational time dilation, a bunch of other stuff that I won't get into right now. So how does this really all affect everything? So at the equator, the Earth is moving about 1,000 miles per hour. And this is because really the Earth it's not a circular shape that you would imagine. It's not kind of conventional circle. It's more of an oval kind of egg shaped where it bulges out in the middle. So in the middle of the Earth, the equator at 0 degrees, you're going to be moving faster than you would be anywhere else on the Earth, north or south. So for example, up at the poles, technically if you were at 90 degrees north or south, you wouldn't be moving. There would be no rotation to the Earth. It would almost be non-existent. That's why if you're up at the top of the North Pole, it never goes nighttime, right? During summer, there's no night. It's all daytime because the sun never passes beyond the horizon. And next slide. So what does this mean? Technically, this means that somebody living on the equator would age slower than somebody living on the North Pole. Now, you won't ever realize and see this in real life. It's way too small of a time dilation to really have any effect or have any notice. Another place we can see this in is space. So the ISS, the International Space Station, travels at about 1,700 miles an hour. Compared to Earth, where if you're living on the equator, you're only traveling through space, or on Earth at about 1,000 miles per hour. So the astronauts in space age about 0.005 seconds slower than the people on Earth. And also because it's not just aging slower as well, all of your bodily chemical processes are also going slower. So everything is slowed down, really. The faster you're going, the slower you age, the slower everything is. So another way that you can think of this is light can't escape a black hole, right? Black holes are so strong that light cannot escape them. They're literally the eater of everything. They suck everything in them. If you were to throw a clock into space towards a black hole, the closer it got to that black hole, the slower the clock would tick, the slower time would move. Now this is because of gravitational time dilation. So gravitational time dilation means the heavier something is, the more mass something has, the greater the gravitational force is exerted upon it, which means it warps space-time. And space-time is space-time, right? So it's a linear plane, as you would imagine in space, and objects with mass create a gravitational well. So the Earth has a gravitational well that sits underneath it, or that the Earth creates underneath it, right? And it's kind of like a drain, so things swirl around it. It's how things stay in orbit, right? It's how we orbit the sun. It's how the sun orbits the galaxy, or how the sun orbits through the galaxy. And then also, like Jasper was saying earlier, the Great Attractor is a supercluster of galaxies about, I think, 100 million times heavier than our sun, than the mass of our sun. Also known as the Laniakea supercluster. And everything in 100 million light years is being pulled towards that at speeds of 600 kilometers per second, which is ridiculously fast. Now, you don't need to worry about that because in our lifetime it won't ever affect us, as well as the universe is expanding so fast that we'll never really reach that, we'll never get there. So it's not too much of a problem. But really, all we need to worry about, and I wanted you guys to learn, is that the faster you travel through space, the slower time goes for you. And that's why, technically, if you were living on the equator, you would age slower than somebody living on the North Pole, or why the people in space on the International Space Station age slower by about 0.005 seconds because they're traveling faster through space than people living on Earth. Now I'll hand it over to Alex.
Okay, hello everyone. So I will be talking about Analemma. What is it? So imagine you get a camera and you place it at a fixed position and you take a picture of the sun every day for a year. So every day you take a picture of the sun and you also have a fixed time. So every day it's the same time. So when you combine those photos, you will see a pattern that forms into an 8 shape. So it looks like that. So that's the Analemma. So how does it work? So when the Earth orbits around the sun, the North Pole is not facing up. So it is tilted. So when it orbits around the sun, it's in a tilted position called as axial tilt or an obliquity. This basically means that the Earth's axis at its North Pole in a line is perpendicular to the orbital plane of the planet. So as seen right here, it's slanted. So top slanted goes around. Why the H shape? So it forms this shape because when the Earth goes around the sun, it's not a perfect circle. It's more of like an oval shape. and it's called an ellipse. An ellipse is basically saying that when it orbits, the distance from the sun changes in various points. So in this area, it's farther away from the sun, that's called an aphelion. And then in this area, where it's closer to the sun, that is perihelion. So when it's at the point of perihelion, the distance between the sun is around 147 million kilometers. And if it's in the point of aphelion, it's around 152 million kilometers. So when it goes around this area, it takes longer to go around. So that's how we have longer days. So during the summer, and then when it's around this area, it goes faster. So the days are shorter. So, not all planets have like the same shape. It just depends on their orbital eccentricity and their axial tilt. So some planets could have a circular shape, or a teardrop shape, or even a straight line. So,
Thank you, everybody, and that wraps up our presentation. Do you guys have any questions? If you do, feel free to raise your hand and let me know. Let us know.
Questions?
Questions, anybody?
Sarah has questions.
Go ahead, Sarah.
This is for Mike, when you mentioned Einstein's, what is it?
Louder, Sarah.
Okay, I'm talking about his theory of relativity.
Mm-hmm.
So basically, I was trying to understand it. What he was implying is that time moves the same thing when you're in a black hole, or it.
Yeah, so the theory of relativity is, and I'm also not 100% sure on it, so I'll give you the best answer I can. It's a really hard concept to like fully grasp, at least I think. So relatively, right, the faster you're traveling through space-time, because it's like a blanket and there's divots in it because of objects with mass. When you travel through a region that is popularly dense with mass, you're gonna be traveling slower because it's just the way it works, right? Things are gonna pull you into them, such with like that gravity well, right? Earth has that gravity well underneath it. So does the sun, and that's what keeps everything in orbit. So if the faster you're traveling, which means faster you're traveling through space-time, the faster, it's really hard to explain, man. Like I was saying with that thought experiment. So if you have two people on Earth, you have two twins, right? One has an atomic clock and they're sitting on Earth. Another has an atomic clock in a space shuttle. They take off from Earth and they're traveling near the speed of light to Pluto. It takes them about 6 hours to get there. When they turn around and come back though, they'll have only aged about 26 years, whereas the person on Earth will have aged about 30 years. This is caused by that time dilation because, and like once again, it's all relative, right? So when somebody is traveling that fast, the way you can imagine it as, I'm gonna use a whiteboard really quick, that's okay. Markers. Can you see over here?
Yeah.
Okay, so this is Earth, and we have our person on Earth, and then we have our spaceship, right? So our person on Earth, if they're looking at the spaceship, and they had this, they could see the way light travels. They would see light traveling at that spaceship in the near light speed, like this. So that's how time, and light is time, right? Because everything you see is a photon. And so photons carry information and they travel at the speed of light. So technically, material speed of light is time, right? So visually, the person on Earth would see time like this, just straight up and down. Because they're not moving fast, everything's relative to them. So with respect to Earth, the person in space is traveling through time like this, right? So this person technically is experiencing time at a slower rate. That's why they age faster. Because if you're here, you're traveling fast, you're experiencing time slower, it's all relative and respective with each other. It takes a really big deep dive to truly understand everything that goes into it. But the basis is, if somebody's in space and they're traveling at near the speed of light, this is what time is going to look like for them with respect to Earth, and then vice versa. So if you're in space and you're traveling near the speed of light, the time on Earth is going to look like this, right? So it's all with respect to each other and in relativity. It's a really hard concept to understand and really master.
Thank you, everybody.